All right, welcome back to class 6. This is video 4. We previously talked about the velocity field. Let's talk about the acceleration field. And there's really the big takeaway that we want to get from the acceleration field is that acceleration is not just the time derivative that we think it is. It also is dependent on position as well. Right? So if we were just talking about a particle, one single particle, and then the Lagrangian method that we used in solid body dynamics. Acceleration is merely a function of time. We follow a particle and we monitor it. That's what we see. But in the Eulerian method, when we're talking about a field, right, it's a function of both position and time, because the velocity is also a function of position and time. It's not just one particle, it's a field of velocities. So the acceleration is the time derivative here of that velocity field. And so we're going to look at a lot of particles, and we're going to have the position of them is going to be important to us. And so we want to take the complete, I don't think derivative, not integral, derivative. So we're going to have an entire derivative of something, and in order to do that, we need to apply the chain rule and think of in terms of partial differential equations. So the total partial differentiation, if we take the acceleration, first we'll say take the partial derivative of the velocity, and that should be a vector, with respect to time. That's fine, but it's not only a function of time, it's also a function of position. It's this velocity field. So we have to take the derivative of velocity with respect to position. But we're doing it with respect to time, right? So we need to do the chain rule here and go dx dt, which we know to be the component u. And then we also do the same thing in the y direction. So we need to take dy dt, and we know that to be v, a little cursive v. And then lastly, we take the derivative with the respect to the z direction. And so we go dz dt, and we know that to be little w. So these represent the components. So if you're going to rewrite this out, right? Therefore, the acceleration is going to be del v del t plus u del v del x plus v del v del y plus w del v del z. Now this is got different names. These parts have different names to them. And if you want to, we could break this down, because these are vectors right here. Each one of these is a vector. So we might want to find the actual components. So we take the x component, the y component, and the z component, and look at them and think of them in those terms. So we have del u del t. Right, that's the x component of this portion right here. But we also have u del x plus v del x. Right, these are all x component things, plus w del v del x. I almost did it right there, and I did a v again. Oops. I think I did that correct. Okay, yeah, I double check. Trying to think my way through this. Okay, so the y component, similarly, and I don't know if I want to write this in class this way right here, but this is going to be u del y plus v del y plus w del y, and then we'll have del w del t. Excuse me. Wow. W del t. So this is how the component changes, but there's also, we have to worry about how these other component changes with respect to the positions. I think I got that right. Let's double check. There's X's and Y's and Z's, X's, Y's and Z's. I think I got that right. Now, as I mentioned, they have different names to them. This is generally considered to be the local component. And we'll see there's something called the material derivative in the next class. I've decided to put it into the next class, I believe. And then we're really not going to apply to it in a little while. It's going to be several classes before we apply it. I decided to kind of follow the order of the book, but I wanted to include these things. This is like for information kind of stuff. But anyway, this portion right here really represents this, and it's called the local time-based component. But now we have the other part is the convective-based, right? And I didn't give it a name, but I guess I could. I think I can write this, the convective component, or the convected portion. It's not a component, so it's a portion. It's going to be U del V del X plus V del big V del Y plus little w. That's not an omega. I tend to make it look like an omega, but that's actually a W, a lowercase w, del V del Z. And this one is due to changes in position. And I think I alluded to it in an earlier one. Well, I could actually just bring this guy back up here. We could find the acceleration because maybe the vector for right here isn't the same from right here. So if there's a particle that moves, or maybe we move from right here to right there, we can see that he's changing. That particle moves from this spot to this spot, and therefore its velocity isn't the same here as it is there. Therefore, there's going to be acceleration taking place. And as we know from dynamics, acceleration isn't necessarily just the speed change, but it's also can have a velocity, an acceleration, component that's towards the center of curvature, right? Well, that's the same concept right here. The acceleration has to be completely described, and so it isn't just the change in velocity with respect to time, it's also the change in velocity with respect to position. So we already kind of have an idea that that's a real thing that we would need to consume. But that's, again, that is from the particle, right? The one we were talking about with path coordinates, where we had a centrifugal acceleration. We now have to think about how they're acting as a field, right? So instead of just as individual particles, think of them as a field of particles or a field of locations where we're looking at particles passing through them, which is the big takeaway or the big concept. So I have a couple examples here, and they're really time consuming and boring. I'm going to go plod through them. I wouldn't recommend necessarily watching all this. I didn't find any better ones, and I wish I had some good visualizations of these, but I didn't have time to create them. I created the other ones myself from old examples, and I put the MATLAB stuff in here, but I didn't have a chance to do this, and I don't know a way to make these any better. So I wish I had better examples. But here's the examples I'm going to cover, and it'll probably take me a little time to write all this down. I doubt I will do this in class. But if you want to know more about this, please watch this video. So there's a velocity field that's given by this. If we could only make this thing, there you go. All right, so it's given by the initial velocity, right, or this is some constant divided by, I think this is a length right here. So some known length, and these are constants right here, right? They're saying that that looks like an L. So VO, L, and TO are all constants, but it's these two constants multiplied by X, which is a variable. So that's the component in the I direction, and then the component in the that's in the X direction. In the Y direction, it's the VO divided by now the initial time, right? So which is a constant. So this is not a variable. Times time, which is a variable. Come on back to me. There you go. and that's in the j direction. So we want to determine the local acceleration, the convective acceleration. Come on, please. Focus. Will you please just focus? I hate you. Okay, there. I don't know if there's enough light in here. That's why it's the overhead light. It's a terrible room. And the acceleration for this flow, right? So we want to have the total acceleration, or not the total acceleration, but the what's described as. So notably, we could rewrite this vector as divided by what, L? X, I'll put them in brackets, I plus VO over TO, and this is times time. Whoop, not that guy right there. Here. All right, so if we want the local one, it's simply going to be the partial derivative of both of these with respect to time, but there's no time term in there, so this one goes to 0, right? So if we want to go del V, del T, all we take is the partial derivative of this one, of course, and this goes to 1, right? So we have VO over TO. That's supposed to be TO right there. J. Right, so that is the answer. And then maybe I'll put some parentheses around this. Now the convective The convective acceleration, as you recall, looks like U del V del X plus V, little v, del big V del Y plus little w del V, big V del Z. Well, none of these are functions of Y, so that's got to go to 0. None of these are functions of Z, so that goes to 0. So we could break this one, right? So this is still a vector. So this actually has an I, J, and K component to it, even though it looks like it's one thing, and with associating with it here, that's still a vector in itself in the notation that we have. So we could break this one guy out by himself to U del X I plus U del Y J plus U del U. Did I do that right? Let me think about it. Don't judge me. Okay, I'm concerned I wrote it wrong. Right, so we want to have all right, so it's my friend calling. But anyway, let me get back on track here. So we're not doing, let's see, here's the equation that we're looking at. We are not doing it with respect to Y. So I'm thinking I'm saying this wrong right here. What I think I need to do when looking at this, I believe that needs to be U times del U. Did I write that? No, maybe I was writing that right. Del U, del Y, but we already said that del Y's are gone. So I want to say that the only way that this could be there is we have to do del X's. So it's going to be del do we ever do V? Yeah, I think it's going to be no, because that doesn't exist. I should just write down what's on my paper, but I'm starting to question. That's my method here. I always question everything I do here. So we already said that V, so no V's times anything. It's going to be U times all of them. So it's only going to be U terms. So it can only be things that are multiplied by U. So it's going to be U del Y. No. Let me just write down what's on my freaking paper right here, and I can argue with myself later on. I think it's del U del Y But I'm saying it's a J term. So that's the thing that's bothering me. So I think it should have to come out of here because this is the guy that gets multiplied by J. So I think we might have already gotten rid of him in terms of the convection terms over here. Is, you know, del U, del Y. Yeah, that's one. Yeah, that makes sense. Del U, del Y, del U, del Z. Sure, I think that's correct. That's my. I'm fairly convinced of that, but we might not worry about it. Anyway, we know that this is not a function of y, and we don't have any functions of z inside this piece right here. So what we're left with, if we look at this, is u, this guy right here, u, which is this term right here, VOL, times x, I can bracket in there, times del u del x, right? Which we know is just going to be v time over L, right? So right here, v over L. And that's going to be in the I frame. So we could say that the total acceleration that we're trying to find up above, right, is going to be made up of two parts. One of them is the local, this is J, so I'm going to do things in order of I and J. And this one right here is going to be VO squared over L squared times X I plus VO over T J. So that's the actual acceleration, but of course it's made up in two parts, right? So turns out this is the time-based one, and this is the position-based one. But this is the actual magnitude of this, well, not magnitude, this is the vector of this acceleration. I've already made this video like really long, and you don't really care, I know. But I'm going to go ahead and with another example in this, and let's see if we could do this efficiently. But maybe not. We'll see. So this is a three-dimensional field. First off, we would note that none of these are functions of time. Therefore, there's no local because there's none of them, because none are functions of time. None are functions of time, so we're going to have completely convective acceleration taking place. So we could just go through them and try to find, using the equations that we have previously noted right here, the u du dx, v dv dx, and w dw dx. And that is not supposed to look like a omega. All right, so taking the x direction, we go u, which is negative x, times du del u del x, which is, of course, -1. And we're going to add that to, remember, this is a component, so we've broken in the i's and j's and k's separately. Next, we're going to take v, so 4x squared y squared, and multiply it by del, write it down somewhere, del v del x, which is right here. We can see that's just going to be 2 times 4x times y squared, right? So it's going to be 8x y squared. Is that right? Oh, no, it's not. Son of a bitch. We're going to take del v. Okay, so actually it's going to be v times del v del x. And I swear I'm going to... We have this is supposed to... you know what? I think this is written the wrong way. I wish I had canceled this whole thing out. Wish we had ended this whole problem, because I think I wrote the problem the wrong way. Son of a gun. Is that true? I think it might be true, because this thing is supposed to be 0 right here, but that's not looking like 0 to me. That's supposed to be AX is V del X. I'm pausing this video. Okay, I misread. my thing here. Okay, so I knew I just need to be a little more organized right here. This should be, when I wrote this, I think I wrote it wrong. Let me rewrite this into the thing. And here is what it should look like. And so hopefully I will fix this later on. Let's see, here's where we went. Okay. These are all supposed to be used everywhere, and I miswrote them. They're supposed to be, yes, I miswrote them. So it's supposed to be V's everywhere and U's everywhere across here and V's everywhere. So let me try to fix it. I know I just don't have time to rewrite everything everywhere. And let me double check my thing here. It should be UVW. All right, so UVW. All right, so happens to the best of us, and it happens to me. And so let me fix this if I can. I should just give this to you. I'm going to plot this out. I'm not writing this out during class. I am not writing this out during class. But I believe it's going to go U, Y, and U, Z. And this is supposed to be, yeah, I think that's the correct way. Man, bothers me. That should be V all the way across. And this should be Y, yeah, Y and Z. Okay, and then so this should be W, 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 and that should be X, and this should be X, that should be Y, and that should be Z. Z. Okay, so this I believe to be correct if we were to break these things apart. All right, and so in that case, when we go to the second component here, we have V times du dy. Well, this has no y portion of the thing, so it goes 0. And then so the next portion right here we go W del u del z, and that has no function right there. So even we have the W of x minus y is still going to be 0 because we're going to take this with respect to z. And what we're going to end up with is the only thing we have is a positive x right here. And in a similar way, if you'll excuse my stupidity here and not getting this the right way, just write down the things that you know. We'll note, oh, I should also have pointed out here that there's a 0 that I should go right in there because it's not a function of time, right? So if I was breaking it down to components, but I guess I already said that there was no local, so I didn't bother writing down the 0 for the local. So if I write down now the u for this, here is the u, negative x, but now I'm going to multiply it by del v del x, and del v del x, that's going to be, that is going to be the 8xy squared, right? So that's the correct one. Plus v for x squared y squared, and that one's going to be times del v del y. Del v del y, so we're going to end up with, I'm still looking at this thing, del v del y, it's going to be 8x squared y, right? Because we're taking the derivative of this right there. And then lastly, we're not doing this in class. That's what I've decided right now. We're going to take the w, x minus y, and we're going to multiply it by del v, no, is that right? Yeah, del v, del w, which is going to be 0. So this one turns out to be 8, once you group things together, 8x squared y squared, 4x squared y, I said minus 1. And I'm wondering why. Because I'm wondering if this guy right here was supposed to be for, that really bothers me. There's a lot of things wrong with this freaking example. I wonder if I could just cut off this portion of the thing. I think I'm going to just cut off this portion and just toss this example because it is terrible. It's a terrible example. We can just look through the back and let's just look at C. This is where the source material came from. I took this from the Coast Guard Academy when teaching at the Coast Guard Academy, and this is problem 421 in this textbook, in that whatever edition of the Munson textbook. And see, I'm showing this right here, that portion right there is wrong. So I need to either fix this or I need to fix that. But I don't see that right there doesn't belong there. It doesn't belong anywhere. But I'm still not convinced. Yeah, I think that's the only thing that's wrong. I think that little guy right there needs to go away, and that would have solved everything. But anyway, blah, 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 blah. This video is too long. No one's ever going to watch it. So right here is the Z component right there, and it just takes up too much time. We're not going to do this in class. We're not doing this problem in class. Not to mention that this was, at the very beginning in this, I wrote, too much material to cover in one class, September 21st, 2016. And this was lecture 12 in the way that we were doing it in that class. But anyway, so these are my notes that I recorded for all of this stuff at the Coast Guard Academy. And this example is trash, so we're not going to do it. So that's the end of this video and all of these videos and the end of class 6. And wasn't this a great experience?